and welcome, and in this video we're going to be talking about something called vertex form. Now, we've already talked about standard form, so we have the standard form of f of x equals 2x squared minus 8x plus 11. And we talked a lot about how we can solve equations like this, how we can graph equations using key features, but in the last video we did talk about transform functions. And those are also very, very useful. Being able to distinguish what the transformations of a function are incredibly useful. Now, if I told you that I know by looking at this standard form that it is vertically stretched by 2, shifted to the right 2, and shifted up 3, and that its vertex actually was the point 2, 3, you'd probably be a little bit confused of how I got it. But it's using something called vertex form. This would be the vertex form of this particular equation. So actually what we were doing yesterday is using vertex form to talk about what the transformations are. But what we need to talk about now is, well, how do we get from here to here? How do I go from standard form to vertex form? Because you can't really determine what the transformations are from standard form. Vertex form is very, very useful for that. Well, it's actually not that bad, and it utilizes something we learned a little bit earlier, which is called completing the square. So I'm going to go ahead and take you guys through how to take something from standard form and convert it into vertex form. That way you can distinguish what the vertex is, as well as all the transformations. Now, in order to get to vertex form, there's kind of a few different ways you can start it off, and there are a few different ways of thinking about it. The first thing that I like to do is I actually like to move the constant over to the other side first. Now remember, with completing the square, we can't have a leading coefficient of 1. So when we are solving by completing the square, we would actually end up dividing everything through by that leading coefficient, but we're not actually going to do that here. What we're instead going to do is use these steps a little bit differently. So the first thing I'm going to do is actually move the constant over to the other side. So I'm going to subtract 11 from each side. Now, I subtracted 11 from each side, and I know this probably looks weird. F of x minus 11? That looks a little strange, but I promise that this is all going to work out in the end. Now, the next thing that we need to do, now remember, normally we would divide each side by the leading coefficient. However, in this particular case, we're actually going to factor out the leading coefficient from everything on the other side of the equation. So I'm going to factor the 2 out of 2x squared minus 8x. Now, remember, this is where we start to actually complete the square. We have to figure out what we're going to be adding to each side in order to create a perfect square trinomial. Now, I normally like to leave a little space open on each side to show that, so I'm going to go ahead and do that real quick. Now, remember how we got what that term was going to be. What we did is we took half of the linear coefficient and squared it. So I'm going to take half of negative 4, which ends up getting us negative 2, and we're going to square negative 2. And that is what we're going to add to each side, kind of. So I'm definitely going to add a 4 in here. However, I'm not actually adding a 4 to each side. What I'm actually doing is I'm adding a 2 times 4. This 4 is technically being multiplied by 2, so we always got to think about order of operations. Multiplication comes first. So what we're actually adding to each side is 2 times 4, which is 8. So I'm actually adding 8 to each side, so I'm going to move an 8 over to the left-hand side. And now what I can do is I can simplify the left-hand side by combining like terms, and I can factor this perfect square trinomial the way that we always would with completing the square. So there we go. I combine a negative 11 and a positive 8 to get negative 3. So I have f of x minus 3 is equal to 2 times a quantity. And this would end up factoring to x minus 2 quantity squared. And remember, half of that linear coefficient is always going to end up being what's inside that squared binomial. And now I'm pretty much done. All I need to do now is add 3 to each side, and I have my vertex form. And there I have it, our vertex form, the one that matches up from the beginning. 2 times a quantity of x minus 2 squared plus 3. That's how we get vertex form. And the reason vertex form is so nice, well, one, it tells us a vertex, hence the name vertex form. The vertex is always going to be the opposite of what's inside and exactly what's outside. So positive 2 and positive 3. And we can also think about why the vertex is positive 2 and positive 3 by thinking about transformations. If we think about transformations, the first thing that happens is that it is vertically stretched by 2. But remember, that actually doesn't have any effect on what the vertex is itself. But if we were to graph the entire function, that would be absolutely crucial to include. The next thing that happens is that we are subtracting 2 inside, which means we are moving to the right 2. Right 2 means x is positive 2. And then finally we add 3 outside, which means we move up 3. Up 3 is y is positive 3. So that's how we can use vertex form to quickly tell what the vertex is as well as all the transformations. So you can probably see why this is so useful. Now, this is a little bit different than completing the square just because a couple of steps are just slightly different, but we're still using the exact same concept. Now I want to go through one more problem to show you the mechanics of how we can go to vertex form. All right, so let's say we had this example here. F of x is equal to negative 3x squared minus 24x minus 32. Now, once again, this is in standard form. We could graph this from standard form, but what if we wanted to know what the vertex is right away? Well, I guess we could do opposite b over 2a. That's not that bad. But what if we wanted to know the transformations? Or what if they were just like, yo, get this in vertex form? Well, we can do that using a fairly straightforward method, right? We're completing the square. Now, remember, the first thing that I like to do is move the constant over to the other side. So I'm going to add 32 to each side. From here, we are going to factor out the leading coefficient. We're not dividing each side through. I mean, you technically could do that, but it might become a little bit messier. But we're going to factor out the leading coefficient from everything on the right-hand side of the equation in this particular case. And remember, that is because we cannot complete the square without a leading coefficient of 1. So I'm going to go ahead and do that. Now remember, we're about to complete the square, so I like leaving a space on each side just to kind of cue me up. You don't have to if you don't want to, but what you do have to do is complete the square. So remember, the way we get that is by taking half of the linear coefficient and squaring that, and that's kinda, in this particular case, kinda what we're adding to each side. So half of the linear coefficient was a positive 4. I have to go ahead and square that. And that's kind of what we're adding to each side. So a 16 definitely does go in here. However, this 16 is actually being multiplied by negative 3. So I actually didn't add a 16 to each side. I added a negative 3 times 16, which is negative 48 to each side. So that's actually what I'm adding to each side. So now I can combine like terms on the left-hand side and then factor on the right-hand side, and that's going to give me something like this. And that's going to end up getting me this. Remember, half of the linear coefficient is always going to be the number inside a squared binomial. That's why it ended up being 4. Also, if you just factor that, you would get x plus 4 and x plus 4, which is x plus 4 quantity squared. And now finally, what we have to do is move the constant back over to complete our vertex form. And there it is, our vertex form. So from here, I can determine that the vertex is going to be negative 4, positive 16. I can also think about this in terms of transformations to get that. I shifted to the left 4, which means x is negative 4, and up 16, which means y is positive 16. And one other thing I want to quickly point out is that notice how the leading coefficient was negative 3. Well, look at what's out in front, negative 3. If you look at the previous problem, the leading coefficient was 2, and guess what was out in front? Positive 2. So that is a connection that you should be making. The leading coefficient is never going to change. It's just going to end up out in front, and it's always going to act as that vertical stretch or compression or reflection if there is a leading coefficient other than 1. Well, I hope this video was helpful. If there's any questions, please feel free to let me know. In the next videos, we're going to be covering quite a few different things. We're going to be covering something called nonlinear systems and stuff of that nature. So stay tuned, and I look forward to seeing you guys in those videos.